Good morning to everyone. Today, I, Prasanna Kumar from CSMC, will be presenting on the topic magnetic levitation principles and applications in engineering physics. In this presentation, I will explain how magnetic forces can make objects float without any physical contact and how this principle is used in modern technology. Introduction to magnetic levitation. Magnetic levitation involves suspending objects using magnetic forces without contact. It eliminates physical frictions, enable high speed and efficient transportation systems. Understanding the basic physics principles is essential for developing levitation technologies. Magic, magnetic levitation or maglev simply means lifting an object using magnetic forces so it floats in the air. There is no touch, no friction, and no wear and tear. This concept is widely used in high-speed trains, engineering designs, and scientific experiments. To understand how it works, we need to know some basic principles of magnetism. Fundamental principles of magnetism. Magnetism comes from the movement of electric charges inside materials. A magnetic field is generated whenever charges move. In physics, magnetic forces follow rules such as Coulomb's rule and the Lorentz rule. These laws explain how magnets attract, repel, and interact with moving charges. Using these forces, engineers can design systems where magnetic force can balance gravity. Types of magnetic levitation. Electromagnetic levitation uses electromagnets controlled by feedback systems. Superconducting magnetic levitation employs zero resistance materials for strong magnetic fields. Diamagnetic levitation exploits materials that repel magnetic fields naturally. There are mainly three types of magnetic levitation. Electromagnetic levitation (EML) uses electromagnets controlled by sensors. Superconducting magnetic levitation, which uses superconductors to create very strong repulsion. Diamagnetic levitation uses materials that naturally repel magnetic fields. Each type has its own advantages and applications. Electromagnetic levitation. In electromagnetic levitation, electromagnets are used to lift and stabilize objects. A feedback system continuously checks the position of the object and adjusts the magnetic force. This type is commonly used in maglev trains, industrial lifting devices, and some engineering tools. It is reliable but requires electricity and constant control. Superconducting magnetic levitation. Superconducting levitation uses materials called superconductors, which has zero electrical resistance at very low temperatures. They show the minor effect, meaning they completely push magnetic fields out. As a result, the levitation is very strong and stable. However, they require cryogenic cooling, which makes them expensive but extremely powerful. Diamagnetic levitation. Diamagnetic materials create repulsive forces against magnetic fields. Levitation occurs when magnetic repulsion balances gravity. This method is used in scientific experiments and demonstrations. Diamagnetic materials like bismuth or graphite naturally repel magnetic fields. If the magnetic repulsion requires becomes equal to gravitational force, the object floats. This method is often used in science experiments, mini levitating devices, and classroom demonstrations. It is safe and does not require electricity. Magnetic levitation in transportation. Maglev trains are a prominent applicant of magnetic levitation technology. They achieve high speeds with minimal friction and turbulence. Maglev systems require precise control of magnetic fields for stability. The best examples of maglev technology is maglev trains. They float above the train, eliminating friction which allows them to reach very high speeds. Some maglev trains reach speeds above 600 km per hour. Precise, precise control of magnetic fields ensures stability, safety, and smooth movement. Advantages of magnetic levitation. Reduced friction allows for higher speeds and lower maintenance. Less mechanical contact leads to increased longevity of systems. Magnetic levitation offers a quieter operation compared to traditional transport. There are many benefits of maglev technology. Almost no friction, so the speed is very high. very low maintenance because there is no physical contact, longer lifespan of mechanical parts, quiet and smooth operation making transportation more comfortable. These advantages are pushing countries to adapt maglev systems. Challenges in magnetic levitation technology: high cost of infrastructure and superconducting materials, complex cost systems needed for stability and safety. Cooling requirements for superconducting levitation systems pose operational challenges. However, there are some challenges. Infrastructure is costly, especially for maglev tracks. Superconductors require very low temperatures, which increases the cost. Control systems must be very accurate. Operating and maintaining cryogenic cooling is complicated. These challenges limit the widespread use of maglev worldwide. Applications in industry and medicine. Magnetic levitation is used in contactless bearings and conveyor systems. It enables magnetic resonance imaging in medical diagnosis. Levitation technology is also explored for precision manufacturing and research. Beyond transportation, magnetic levitation is used in many fields. Contactless bearings in mechanics in machines reduce friction. Magnetic conveyor systems for smooth transport of goods. In medicine, MRI machines rely on strong magnetic fields. Precision making manufacturing uses maglev to avoid vibrations. Magnetic levitation technology is slowly entering more industries. Magnetic levitation is in energy storage. Magnetic levitation can support flywheel energy storage systems. It reduces mechanical wear and increases efficiency. These systems are used in power grids for stabilization and storage. Magnetic levitation is used in flywheel energy storage systems. Because the flywheel floats, there is almost no friction. This allows it to store and release energy efficiently. Such systems help in stabilizing power grids and balancing renewable energy sources. Scientific research and demonstrations. Diamagnetic levitation allows study of materials in weightless conditions. Magnetic levitation is used to simulate zero gravity environments. Such experiments advance understanding of material properties and physics. Diamagnetic levitation is widely used in scientific studies to simulate zero gravity conditions on Earth. This helps researchers test materials, biological samples, and physics experiments without gravity's interference. It also allows students to understand magnetic forces better. Future trends in magnetic levitation. Development of room temperature superconductors could revolutionize levitation. Integration with renewable energy sources to power levitation systems. Expansions into new sectors like aerospace, robotics, and urban mobility. The future of maglev technology looks promising. If scientists develop room temperature superconductors, it will revolutionize transportation. Maglev can be integrated with renewable energy systems. It may expand into aerospace, robotics, and urban transport. Research is ongoing to make maglev cheaper and more efficient. Magnetic levitation in space applications. Levitation principles could enable frictionless space components. Magnetic propulsion systems may facilitate spacecraft maneuvering. Research is ongoing to adopt levitation for microgravity environments. In space engineering, magnetic levitation could help create frictionless machines that work smoothly in microgravity. Magnetic propulsion could become an alternate become an alternate for spacecraft movement. Scientists are exploring how maglev can be used in satellites, docking systems, and robotic mechanisms in space. Environmental impact and sustainability. Magnetic levitation reduces greenhouse gas emissions by enabling electric transport. Energy efficient operation minimizes environmental footprint. Material sustainability and recyclability are key considerations for future systems. Maglev transportation reduces pollution because it is electric and has very high energy efficiency. Less friction means less energy is wasted. Future systems may use recyclable materials and sustainable cooling methods. Overall, maglev can be a clean, environmental friendly technology. Magnetic forces can be manipulated to achieve stable levitation. Different types of levitations are suited for specific applications. Advances in materials and control systems drive innovation in the field. To summarize, magnetic forces can lift objects without contact. There are different types: magnetic, electromagnetic, superconducting, and diamagnetic. Each type has unique benefits and applications. Advances in materials and control systems continue to improve the technology. Challenges and opportunities. Overcoming high costs and technical complexities remains a priority. Emerging technologies offer potentials for broader adoption. Collaboration across physics, engineering, and materials science is essential. In conclusion, magnetic levitation shows how physics can be applied to real world engineering solutions. From transportation to medicine and scientific research, maglev has the potential to transform many industries. With continuous innovation, it will play an even bigger role in the future technologies. Thank you for listening.